Okay, so now what do we do when we can't get the same base? We have to use logarithms to solve. That's the whole reason for doing the logs, is really to solve exponential equations like this. And you've actually kind of had a preview of this, so that's good. 2 to the x equals 5. Okay, so it's very clear to me when I'm looking at this, trying to solve it, I'm not going to get 2 and 5 to be written as the same base. It's not going to happen. So you then would take the log of each side, and I'm going to hand back the quick quiz today, which you all did awesome on. So you take the log of each side like that, and then there's a property of logs that lets you bring this exponent down so that you can access it. So x now, instead of being in the exponent, becomes the coefficient. It goes right in front. That was the power property. So, and then we're almost done. This is just a constant. Log 2 can be done on your calculator. So you just take log 5 divided by log 2, and if you do that, if you evaluate it properly, you'll get 2.32. We'll round to the hundredths place is fine. And we want to double check and make sure that makes sense. 2 raised to the 2 power is 4, so we know it needs to be a little bit bigger than 2. So 2.32 makes perfect sense for that. Let's try, we're going to do one more example like this with e in it. Remember, e is just a constant. Do you remember what e is roughly? 2.7 is close. So let's solve this equation. And okay, this says 4e raised to the negative 0.3x minus 7 equals 13. Okay, that's an exponential equation. We want to solve for x. X is in the exponent. It's an exponential equation. We want to solve. So the first thing you want to do is isolate this part, e to the negative 0.3 to the x. That's the hard part. So let's unwrap it. Let's get rid of the minus 7, and let's get rid of the divided by 4. Let's just, undo those, because we want to get to the x. You can't just start out taking logs of this. That'll make it harder. And besides, it's not log, it's natural log. So let's add 7, negative 0.3x. Are there real things that are modeled by this equation? Yes. You'll see. So add 7, you get 20, and then divide by 4. So you will greatly simplify your life if you start by simplifying the equation. Okay, now, since we can't get the same base, I would love to be able to, but we can't. You don't take the log, you take the natural log. You want to undo e raised to a power, which is why we practiced with these expressions. So you're going to actually take ln, natural log of each side, equals natural log of 5. That's something that you can do on your calculator. So now ln and e to a power are inverse operations. They undo each other, and lo and behold, negative 0.3x is now accessible to us because it's not in the exponent anymore, because these undid each other. We practice simplifying these kinds of expressions. We're almost done with this problem. So the ln, you can basically like cancel those went away. They're inverse operations. They undid each other. And we just divide by negative 0.3. So I know it looks different. This is a different kind of expression, but that will give you an answer. If you do natural log of 5 divided by negative 0.3, and you'll get negative, you should get negative 5.36. This is close enough. Okay, now let's see an application of these, and you don't need to write this down. This is from, I'm going to show you example 3 on page 516, because a number of your problems from your homework set, you'll have to follow this Newton's law of cooling. So this is a science example, and you don't have to copy it down because you'll see it right here. I'm going to zoom in. This is page right here, example 3, okay? So this formula right here when you do your problems, there we go. So car, okay, so this Newton's law of cooling, it doesn't tell you this equation in the problems that you do, so you have to go back to this page and pull up this formula. But let's do a real science application here. So you're driving on a hot day when your car overheats and stops running. It overheats at 280 degrees Fahrenheit and can be driven again when it's 230. When it cools down from 280 to 230, the rate of cooling, R, is a constant given by 0.0048. And then the temperature outside, of course, has an effect on cooling, so it's 80 degrees Fahrenheit outside. How long in minutes do you have to wait until you can continue driving? So here's the Newton's law. You fill in the temperatures, 230, 280, and 80. So you substitute those. Those are just constants. T naught, T sub R, and R. You fill those into the equation, and you're going to solve for t. You want to know t time, but notice it's an exponential equation because the variable's in the exponent. So you get the e raised to a power by itself by dividing by 200, and then you take the natural log of each side, so the natural log and the e go away, and you're just left with the exponent, negative 0.0048t, and you just divide by the constant, 0.0048, and you get roughly 60. So you have to wait an hour, 60 minutes. You have to find something to do so that you can continue driving your car when it's the right temperature.